Yep. So thank you. Thank you for the opportunity to indeed sort of finish my talk. It's a bit more than that, but okay. So let me just it will be independent in the sense that I will record in the first 40 seconds what you have missed if you were not at the first time. So semi-independent. So the idea was that, as the title suggests, I want to, there won't be any technical results or like any theorem or anything in the talk. It's just I want to present an idea. I want to present like a method, a way of thinking. And that's how to view monoidal functors as a way to construct graded rings, graded algebras. And was as give examples of how to use it in certain situations that I'm interested in. And so recall that when you, okay, I spent last time, so I will assume that now everyone knows what a monoidal functor is. Okay. So just the notations. So okay. So if I have two monoidal categories C and D, so first, I will write just home C P like this. This is just the category of functors, just functors. So the fact that the monoidal doesn't play any role here. Then if I add a tensor symbol here, I mean monoidal functors. Okay. So if I just write it this way, this means strong monoidal. And if I write it this way, home lax. Maybe I should put it in blue too to be clear. Those are lax monoidal functors. Okay. And if I add an S here, that means that they are symmetric. Okay, those are some my notations. And what I explained last time is that there's a way to view graded abelian groups and graded rings as examples of things like this, especially if N is a commutative monoid. I can consider what I'm going to write brackets M is just a discrete category with set M, and it becomes a monoidal category from the product in X. So it's a discrete. Okay. A discrete category is basically a set, and a discrete monoidal category is a monoidal set, which is monoid. Okay. And then I explained that there's with my notations. There's so first. So a functor from M to the category of abelian groups. What is it? It is a discrete category. So a functor is just sending each object to each object, and there's no extra condition. So it's just a family of abelian groups indexed by the elements here. And I choose to see it as, let's package all of them into a direct sum. And that gives me an M-graded abelian group. There's no harm. Basically, an M-graded abelian group is nothing but the data of each component, right? Because there's no superstructure. Now, I look at the lax monoidal functors, then this gives me M-graded rings. If I add an S here, then it's commutative. Okay, so by that, well, the extra data corresponding to the functor being monoidal exactly means, if you remember like what that monoidal means, it exactly means that you get maps from, so let's say that M is, let's say, additive in notation. Okay, the data of being monoidal exactly gives you things like this. Okay, and that's exactly the data that gives you a ring, right? And the properties of monoidal functors have to do with associativity, which exactly means that this is associative, etc. And the fact that it is symmetric exactly means it is commutative. Just an exact translation on both sides. Another way of seeing it is that when C and D are monoidal, this is also monoidal category. Like there is a tensor product of functors called the Day convolution. Technically, the slight assumptions on D for this to work. This could be monoidally co-complete. Okay, the category of Abelian groups satisfies all this. I will ignore this issue. Here, this has a tensor product, and the monoidal functors are exactly the monoid objects. Like monoidal functors are the monoid in the category of functors. And so on both sides, if you compare this, this is exactly like sort of like an equivalence of monoidal categories. And so here, the monoid objects inside of here are exactly the monoidal functors. And here, the monoid objects inside the category of graded groups are graded rings. Monoid inside groups are rings. So this is all very consistent. And so this tells you, and like, okay, I can see graded rings as monoidal functors. You might say, oh, but I had an object that I understood and I replaced it by an object that I understand less. So is that useful? And I try to convince you that sometimes yes, maybe not always, but so the first thing is that I want to argue that this is actually a better way to understand graded abelian groups and graded rings in the sense that the heart of what is an abelian, a graded group, is not this direct sum. It is the data of each component. And likewise, what is a graded ring? I argue that it is more true to the idea of a graded ring to say that it is the data of all its components and the products between them than this direct sum of components. So that this encodes more faithfully what it means, what actually a graded ring is. In particular, I don't think I explained that last time, but when you work with graded rings, you want to work only with like homogeneous ideals or things like that, and that only defined in terms of the components. Like this direct sum is actually distracting you from what you really want to work with. Like it gives you a sense that, oh, this is a ring with extra structure, but actually this ring is distracting you. It has ideas that you don't want to consider. It has a lot of things like, for instance, what is a graded field? Well, a graded field is a graded ring in which every homogeneous element is invertible. The fact that there are lots of elements here which are not homogeneous, sums of homogeneous, they're just distracting you for what you actually want. It's just the homogeneous elements are actually relevant. Okay, so that's just what I. Okay, so let's look at K-theory. So I'm not going to define what K-theory is. I'm just going to say what I want to say about it. Basically, the story is that the K-theory of a ring is just a group, but the K-theory of a commutative ring is a ring, which is better. So why is it? Like, why do we only get groups, but for commutative ring we get rings? And how can we slightly enhance it to still get rings for larger class of base? Okay. So let's R be a base ring, commutative ring. So it could be Z if you want like to not have a basis, basically. And let A be our algebra. So by that I mean associative with unit. Then you can consider A is the category of finitely generated projected A modules. Say on the left, for instance, doesn't really matter. And then you can consider K0 of A is the quadratic group of here the set of isomorphism classes of A with direct sum. So if you have finitely generated projective models, you can take the direct sum. That gives you sort of monoid structure on the set of isomorphism classes, which is indeed a set because it's finitely generated. But that's not a group. So you take the quadratic group, so you add four more inverses. Okay, so that gives you a Abelian group. So this one is sort of easy to understand, not necessarily easy to compute, certainly not, but at least easy to understand what's going on. So for instance, when A is a field, or more generally a division ring, well, any finitely generated, I mean, you can even remove projective in that case because every module is free. So they're just vector spaces of finite dimension. So they're just classified by dimension. So this monoid is just M, and you add it inverses, so that's just Z. Easy case. In general, it's very difficult to compute. But even more difficult is that you get higher K-theory groups, which I will not define. You get higher K-theory groups. You can describe K1 rather elementarily. Just you take GLN of A, you make n go to infinity, take the limit of the GLNs, which you see as included in each other by blocks, and then you go that to infinity, that GL of A, and you take the Abelianization. So that gives you an Abelian group, and that's K1. K2 can also be described, it's starting to get a bit more annoying, and starting from K3, I'm not sure even for K3 someone has found like a elementary description. Maybe there is, I don't know. But certainly for K4 it doesn't exist, and then you have to use Quillen's machinery of K theory, which I will definitely not get into. And so the point is that they are from our algebras to be groups. Okay. Technically, just for rings to be inputs, but I like to have a base ring usually. Okay, why is that a functor? You can simply take on A0. Suppose you have a morphism from A to B, then any A module, you can extend the scalars to a B module, the tensor product of B. That gives you a B module, which is again projective. So it's something from P of A to P of B, and that induces something from K0 of A to K0 of B. And that extends to all N. But of course, since you don't know how it is defined, then I don't need to tell you how it works. Okay, so the point is that it's a field. And what you can do is that you can package it into a single functor, which I will call K alpha from first to, I write it this way. This is n graded abelian groups. And you take A to the direction. Okay. And of course, if you, yeah.
Just out of curiosity, do we know sort of the role that A plays in K08 for the class of A? Or is that not easy to see in general?
The role that A plays.
Yeah, so A, the algebra itself, like elements of the.
Oh, yeah, okay, yeah. So, yeah, it's so usually you have inside it, you have the free models. So you get something like you get something from n to this given by the free model. So you
Yeah, okay.
and you have a sort of like a copy of Z inside this, which is generated by the class of A.
Yeah, no. Yeah.
And you also conversely sort of like have a morphism from this to, let's say, Z if it's connected, taking by the rank. So you have a connection this, and then you do have some sort of interplay with it. Of course, usually you have more modules than three. So
Yeah.
But then you have
Little streets.
But it's usually not a generator. Sure. Yeah. Okay. So I can just package them into a single functor if I want to. Okay. But of course, if you listen to me earlier, you said that we should not consider this direct sum, just consider the family of the Kn. Okay. So the thing is, so that's a graded abelian group. When A is commutative, this is a graded ring. Graded ring, but commutative in the sense of graded commutative, you know, for the signs that appear. But particularly, it's a ring. So in fact, in particular, this means that for R, when A equals R, this is a graded ring. Okay, so in general, A theory of A is just a gradient module. But when A is commutative, it's a commutative. Okay. So why is that? Where does this ring structure come from? So basically, the idea is that at the level of this category of projected modules, you get something like this. If you have a projected A module and a projected B module, then you get a projective module over A times B. Just take M, then we take the over R. A acts on this factor, B acts on this factor. And when M and N are projective, this is projective. But I didn't write it. Okay. So we get something like this. And this induces, okay, by general machinery, of course, again, I'm not explaining to you how the Kn are defined, so this is all under the rug, but it induces okay. When N and M are 0, it's very easy to see. K0, remember, is just like basically isomorphism classes. So you take, really, it's just this, right? You take an A module and a B module, and that gives you an A times the B module. And it's compatible with equivalence with isomorphism classes. Okay, but in general, you have some checklists. Okay. So why does that imply that we have a ring structure? So, for instance, let's say that A equals B equals F. In that case, what happens? Then this is R tends to R. Well, this is just R, right? So you do get this graded ring structure. Okay. So of course we need to check that it is associative and everything. And in general, when A is commutative, so that also explains to you where the modules, the R module structure comes from. If you just replace, for instance, B by R, then this is A tensor R, this is just A. So that tells you how Km of R acts on Kn of A equal to Kn plus M of A. Explains to you this graded module structure. And what happens when A is commutative? Well, we get Kn of A. You go to something like this. And when A is not commutative, this is the end. But when A is commutative, you can compose it with the morphism induced by multiplication. You say that mu is the multiplication map. When A is commutative, the multiplication map is an algebra morphism that's specific to commutative algebras, commutative rings. In general, this is just an R module map, but when A is commutative, it's an R algebra. So by inferiority, you get something like this, and that induces your ring structure. Of course, you may notice that I sort of took a tangent because I just explained how it goes for R, but when A is commutative, I can just do the same thing with A instead. Right? So I have sort of here two ways to see K star of A as a ring is do this by assuming that A is the base ring, or do this and use a multiplication map. But this is the same thing. Okay, I just sake of not making anyone confused, in case you were wondering this, there's a easy commutative diagram that tells you what is what. Okay, so you can, if you start with Kn of m times Kn n, okay? So what you can do is, as I explained, because I mean the K-theory group is not really defined relative to R. It's just defined on the ring A. So you might as well, when A is commutative, you might as well replace R by A. You're allowed to do that. But you can also say, no, no, I want to take all my tensor products with respect to R. And then, only then, I take the magnitude by multiplication, and that can, so it's same problem. Okay. So this thing here tells me that K-theory is more than just a functor, it's a monoidal functor. Because that tells me that if I package this, okay, so let's say that I take some n, okay, then let's consider all pairs p and q such that p plus q equals n. I can just package all of these maps like this, and that's exactly the n components. Okay. So in particular, that defines me. By taking the direct sum of all n. Examples. Okay. So that's the definition of what are the tensor product of graded objects. Okay, so the fact that this ring structure on K-theory just comes from the fact that K-theory is a monoidal functor. So if you don't want to bother too much with K star and the grading on K-theory, you just want to think about K0, it's fine. Okay. Everything I say will still be just as interesting. It's just like if you're more interested in higher K-theory, it also works with higher K-theory. So and K0 is just monoidal to groups, and K star is monoidal to n-gradient groups. And that explains in itself why, so in general, if you just plug in an algebra, it gives you back a distributed group. But a commutative algebra is a monoid inside the category of algebras. Okay, so that's sort of like an anthem. It's being a monoid inside the monoids is being commutative. That's already something that I had a bit explained last time with this hierarchy of the properties stabilize after some amount of time themselves, and you always end up with something which is as commutative as possible. Okay, but that's just like an abstract explanation. A monoid like this is transported to a monoid here. So commutative algebra is transported to gradient. Oh. So now we understand why K theory, let's say K0, for instance, if you're more comfortable with just K0 of something commutative is a ring, but K0 of something non-commutative is just a ring. So the thing is that, okay, is a ring, if it's even a commutative ring, I did not here study the commutative part. Let's just do it for K0 to simplify notations. It's also so here you take the switch morphism. Here you take the morphism induced by the switch morphism on the level of algebras. And that commute. From the definition of K0, it's kind of obvious. For Kn, of course, it's a bit less obvious, but again, I have not defined Kn, so trust me. But so this tells me that it's not just a monoidal functor, it's actually a symmetric. It respects switching, and that means that if you are a commutative, like if you are a monoid inside here, you actually a commutative algebra, so you actually automatically a commutative monoid, and so you transport it to a commutative monoid here, which is just a commutative graded ring. Okay. So all of this is explained just by this fact. K theory is a monoidal and symmetric functor. Now, if we start with an algebra which is not commutative, what can we do? Not as good, but we can still, like, if we really want a ring, like, let's see where things break. Here we saw that we could do this always. It's just this step that we can only do when A is commutative. So you see that you can go from A, I get something in A and something in A, and you get something in A tensor A. And you can do that again. And now if you have something in A and something in A tensor A, you get something in A tensor A tensor A. Okay? So you can multiply elements, but the price you pay is that you get higher and higher tensor powers. Okay? So what you can define for any A, let's define, so, okay. I'm going to use the letter K to denote either K0 or K star, whichever one, okay, it doesn't matter to me. It's just that with K-star, the issue is that I'm going to have two gradings because I'm going to introduce a new grading, so that will be n times n graded, and the two gradings are not really on the same level, so I don't want to think about it too much. So K just means one of those two, okay, and it's monoidal. And now let's take all the tensor products of A and let's put them all together. Now, this becomes a ring, sort of like in an obvious fashion in some sense. It's just that because I have from the fact that K, whichever one it is factorial. Something like this, and that tells me how to multiply elements in here. Okay? That becomes an n-graded ring. Sort of in a boring way, but it does work. Okay? And you can always do that. Like that just that I did not use any specific thing about K theory, just the fact that it was monoidal. In general, as long as you get some monoidal functor like this, okay, from abelian groups, or I mean, you just take some category, abelian groups, graded abelian groups, some monoidal, let's say abelian category, for instance, but really, so you can define like this. Let's say abelian groups. Okay, and this one. Okay, so it's sort of like not really interesting or powerful or anything. But now, if you try to analyze what's going on in terms of understanding of graded rings in terms of functors, we can understand this in the following fashion. So we have our category C, okay, which in our case is our algebras, but it doesn't really matter. Here our functor, which is a monoidal. And we got at the end, what we got was an n-graded ring, which, as I said, it is just the same thing as a monoidal functor like this. And so the way we constructed it, if you follow, is in this manner. Okay? Here, for any choice of object A, I can just send n to A tensor n here, and that's just kind of like just follow the definition. That's a strong monoidal functor. This one is. This one is strong monoidal. This one, I assumed it was lax monoidal. Okay, and so the composition here is lax monoidal. So, okay. So the point of this is that you can sort of separate this construction into two parts. There's one part which is just you have your functor k, which you care about. Might be K theory, might be something else. I will mention like a bit hermitian K theory. You can have many variants, but like any monoidal functor. And then you have something which really happens inside of C, which is really independent of K. It's just really you delving into the structure of C. And here you're not going very deep into it, because that's sort of like trivial. You can always do this in any monoid category. It's kind of like the equivalent of the fact that if you have a monoid, having a monoid morphism from n to your monoid is just picking an element. Because n is just a free monoid on one element, so you just send your generator to any element that gives you monoid morphism. Here it's kind of the same thing. Here you just take one to some object, A, and now you want it to be strong monoidal, so you need to take n, which is 1 plus 1 plus 1 plus 1, to an object which is isomorphic to A tensor A to tensor A n times, which is this one, for instance. So you don't really have any choice. Okay, so actually, C is equivalent to the category okay. And that should be a reminder of the fact that if you have a monoid, okay, and is isomorphic canonically with the monoid morphisms from n to m. Okay, and the categorical version. So any object of C can be like sort of upgraded to a functor from n to C, and I just need to compose it with my k, with my favorite k, and that gives me a upgraded rate. So that's sort of like recipe. And now we can say, okay, but maybe we can do a bit better than n. Okay, n was the trigger case. N is the case where I don't need any property, I don't need anything specific. But maybe I can do a bit better if I have more hypotheses. First, I can take a look at commutativity. Like, can I expect that this ring is commutative? Okay, so this one existed for any A. So if I want, okay, can this thing here be commutative? It's sort of obvious that when A is commutative, it is going to be commutative, but is it pretty more general? So I know that this one, I assumed it was symmetric, right? If I can assume it, it's true for K theory. So and for this to be a commutative gridded ring, this would also need to be a symmetric functor. So the question is this one symmetric, right? It's not truly necessary. Like you can have a composition which is symmetric, but not both of the components are symmetric. That can happen, but there's no reason for it. Like you cannot expect it. So what you would expect is that okay, is this symmetric? And the thing is that it's kind of hard for this to be symmetric. This is a strong condition for this to be symmetric. Because if you look at what being symmetric means, it means that here the switch morphism should be transported to the switch morphism here. But here, this is a discrete category. All the morphisms are the identity. So if that is true, that means that the switch morphisms in the image are also the identity. So this, let's call it F. Let's say F index A because it depends on A. This functor, so it's strongly monoidal, but it is symmetric if and only if the switch morphism is the identity. And that's a strong condition, right? So if C is a category of algebras, this means that A is commutative. Just take a look at what it means, and it means that A tensor B is equal to B tensor A, and then you can apply multiplication on both sides, and it tells you that A times B is equal to B times A. So it's like, I mean, maybe it's not a shock. Like, okay, I knew that when A was commutative, it would work. There was little chance that I could get any better. But what you can do is that, okay, you don't have to work in the category of algebra. You can allow yourself a bit more leeway, because K-theory is not just functorial with respect to algebra morphisms, it's also functorial with respect to Morita equivalences, which has more flexibility. So has a natural tendency to do that. What you can do is, again, let's look at it not as a functor on R algebras and R algebra morphisms, but let's switch the morphisms to Morita equivalences. So I introduce this category, the Morita category of R. The objects are algebras. Are okay, so I'm not going to delve too deep into it because I don't want to spend too much time on it. Just this makes sense. Okay, so the thing is that it's not strictly speaking a generalization of my previous category, because here I only keep equivalences. So not all algebra morphisms, of course, define equivalences. Usually only isomorphisms do. The problem is that K-theory, so it's functorial with respect to all algebra morphisms, but it's not functorial with respect to all Morita morphisms, just with respect to Morita equivalences. So we can sort of like take a best of both worlds and have a category which contains all algebra morphisms and also all Morita equivalences, but I will want to defend that. For us, that's enough. Okay, and so in that case, if they take the category of algebras with just isomorphisms, okay, I just keep the isomorphisms. Then K-theory factors like this, okay? Which is just a fancy way of saying that K-theory is functorial with respect to monoidal. Okay, and the point is, so what is the point? Is that it's a bit less it's a bit less difficult to be the identity in this category. Like, because so any automorphism of algebra induces an automorphism as a self-equivalence, but it's not injective. So fact is an R algebra automorphism induces the identity with a category if and only if it is an inner automorphism, which is of course like a lot less difficult to be than just being the identity. In particular, if I look at this, now if I want to play the same game, but I replace C with this Morita category, which I can do, I don't need A to satisfy that this is the identity. I just need it to satisfy that this is inner. So is commutative at least one, not necessarily only one, but at least one. Okay, the switch morphism here is inner. So you might say, okay, but does that actually happen? And the answer is yes, it turns out it happens for Azumaya. Okay, so Azumaya algebras have magical elements. I mean, technically, if A is Azumaya, then A tensor A has a magical element called the Goldman element, and it's almost characterized by the fact that indeed conjugating by the Goldman element switches factors. Okay. It's a very remarkable feature of Azumaya algebras. I'm not really sure if it characterizes them, maybe with a few more hypotheses, maybe if you assume that A is itself a finitely generated projective or something. I'm not sure exactly what but I'm not really aware of another class of algebra which has its properties except for Azumaya. Okay, so for Azumaya algebras, this ring might not be super interesting. Like it's not. You feel that you're not using the full structure, but this is cumulative, right? And it's really special. Like to my knowledge, only happens for Azumaya algebras, or rather to rings which are Azumaya algebras over something. Because again, this is just like, for instance, it's true when A is cumulative, it's Azumaya over itself. So Azumaya should be seen as a weakening of being cumulative. Anything cumulative is Azumaya over itself. And sort of Azumaya has this sort of, it keeps a strong symmetry encoded by this property. But it has in some sense close properties to being cumulative. It's reflected in this way. Okay. So now can we do a bit better than N? Okay. Because if, for instance, we're thinking about, okay, let's maybe think about algebras, okay, they came up somehow naturally. Make sure they came up somehow naturally. But maybe let's focus on them. Inside the Morita category, they are exactly the invertible objects. Okay, or weakly invertible objects. Okay, so and after that, a definition of Azumaya algebras. That's what I call being weakly equivalent, that you have a weak inverse in the sense that A times B is not equal to, but isomorphic to the unit of. So inside this category, they are very naturally defined. They are the invertible ones. And so let's maybe let's replace we call it our category of this probably underlines just the subcategory with just Azumaya algebras. We don't need to, but let's simplify things a little bit. Okay, so we saw this game with n. We saw that it meant that if we choose any object in C, we can sort of promote it to a monoidal functor from n to C. Okay? If we try to replace n with something else, this could be what we need. Okay, so let's define P0, pi 0 of C. That's the set of isomorphism classes in C. Yes, I said set, so let's assume that C is not too big. Okay. And wait, since C is monoidal, it's actually a monoid. You can multiply classes by using the monoidal product. And so we might ask the question. So let M be, so I'm going to assume commutative monoid. And every morphism be lifted to truncated monoid. Okay, so it's sort of like the equivalent question. So we said that when m is n, the answer was yes. Okay, that's basically what we said. But when m is anything, the answer is not always yes. Usually there are obstructions to doing that. But, and that's sort of like the only real theorem, which I will of course not prove, but I will state. The answer is yes when the elements in C have this property. So I'm going to call this something. Here we say that A is strongly symmetric. So the theorem is that the answer is yes. Okay. Of course, technically, you don't need all elements of C, you just need the ones whose classes are in the image of this, right? Everything here happens in the subcategory with objects, the elements in the image here. You don't need all objects, but particularly if all objects satisfy this, then you don't have to think about it. But the answer is yes, and in that case, this is actually symmetric. So you can even lift, like it's sort of maybe a bit counterintuitive or something, but you need some commutativity property, some symmetry property to be able to lift at all. And then in that case, it's actually automatically compatible with this commutativity. Okay, so good news is that the C that I'm thinking about, I just said that all elements have this property. All Azumaya algebras have this property. So in my case, it's fine. So in particular, is this Rawa category. Then by definition, the set of isomorphism class in here, so it's a set of Morita equivalence classes of Azumaya algebras that has a definition, that's a Brauer group. And any monoid morphism from some commutative monoid to the Brauer group can be lifted to something like this. And you can even choose, like you can even, so here you send every element here to some equivalence classes. You can choose, you can send here every element to any representative. You can choose your representative as you want, and you just need to modify the transition maps, but you can choose any representative. It's very flexible. Okay. In particular, what I can do is that if I start with one algebra, here I used n. I just said that, okay, I have one element in the Brauer group, then I can use that element to construct a morphism from n to this. But it's a group. So it's just not just n, it's z. Right? It's a group, so it's an invertible element, so okay, z. And actually the Brauer group is a torsion group. So it's even z mod n. And that's already a bit more interesting. Because that means that A is then it's a torsion element in the Brauer group, and then I get Z mod n Z graded ring, commutative ring where K is K0, or K is even itself K star, so it's even n graded, and you get something which is Z mod n times n graded. Okay, and so you can do things like this. In particular, when A has an involution, then it's two torsion. Involution of the first kind is two torsion. And in that case, you can even add on the category, you can add sort of like you can take into account the involution and say, I don't just take Morita theory, I take Hermitian Morita theory. And the thing is that this general machinery is sort of agnostic in which category you're working with. See, the hypotheses are very simple. You just need monoid categories, and the only time you need a hypothesis is this one. You just need the elements to be strongly symmetric. But Azumaya algebras with involutions are again strongly symmetric in the Hermitian Brouwer category. So you can again play this game. So the moral of this story is that you get something by separating the facts. On one side, you have this okay. So to get something n-graded, you sort of separate things by, I have one functor which I'm very happy with, which can be some flavor of K-theory or whatever. And then I need to work really on understanding if this sort of thing can happen. And that's really diving into the structure of my category itself. And then just compose and then you get great stuff. Okay. And so that's where things happen. But that's the idea.